Okay, sorry for the delay. Um, so, couple of things. Now, I know some of you are waiting for your orders to arrive. So, if you, I think this stuff should have arrived over Friday and Monday. I was out of town on yesterday, so come and check with me, and most likely stuff is here. Second thing, later this week. So the rest of the course, the way it will evolve now is the following. I'm pretty much after this topic, I'm done with my lecturing. Um, so we'll have two guest lectures. One again with my students Cheng Wang and Bozang on Android deep dive, so under the hood. So that's on Tuesday, and then the following Tuesday we'll have a lecture with one of our postdoc, Yasser Shokri. So he's going to talk about some of the security issues in embedded systems. The remaining lecture slots, we are going to have you guys present. So by the end of this week, I'm going to hand out some topics. And so if you recall, one of the elements of the course was for you to make presentations on different topics. So we are going to be doing those. If you have your own ideas, send them to me over the next couple of days. And of course, in that case, they're yours. But otherwise, you pick from my list. Yeah.
What was the presentation length again?
What's the presentation was?
What length are you expecting the presentation to be?
I had, depending upon the team size, I had different recommendations. If you do solo or team of two or team of three, if you look at the very first slide, I forgot, but I think it's like 12.5 minutes per person or something like that. Like, okay, so if it's a 2-person slot is twice that. So roughly speaking, if you're doing a 2-person thing, you aim for around 25 minutes or so. Okay. I think I might revisit it because I didn't have an idea at the time I was doing this that how many students would be in the class. So I was going by a guesstimate. I think I might be able to give a little bit more relaxed time than what I had originally, because the class size is, I think it's 25 or something like that, people enrolled. Okay. The other thing is we'll have a homework which would be based around the time synchronization. So originally I had said that you guys have to buy the platforms, but then since the class size has shrunk, so I'm basically going to hand out the platforms. The hardware, you check it out, do it, return it. Okay, so that's how that's going to work. Okay, and then I had announced it previously, but just to emphasize it again, when it comes to project, instead of in-person presentation, it would be you make a YouTube video and include that on your website, as well as, of course, any of the work that you have done. So no in-person presentation, but if you think an in-person presentation is going to make a big impact or impression on me, then do it before June 6th. It may be an intermediate presentation, that's fine. But the reason is June 7th through the next few days, I'm not here. So that's part of the reason I'm also doing the remote stuff. The final thing is that usually there are always 1 or 2 groups who need some additional time for finishing the project, or it's kind of always that trade-off between what you are submitting or not. So I'm pretty liberal about letting you take an I grade, incomplete. Those of you who are not familiar with it, incomplete basically means you have work still remaining to be done in the course. And the way university treats it is as follows, that it appears as an I grade on your grade report, and it will continue to appear as an I grade until the end of the first regular quarter after the quarter. So like, for example, at the end of until December, at which point in time, if you still haven't completed, then it starts showing as an F. And then whenever you actually submit your work, it becomes the actual grade. Now, having said that, I thoroughly discourage taking an extended extension. So you're sort of, if the stuff remaining should be something you should be able to wrap up within the next month or 2 and not leave it for long, partly because if you're in a team, your partners may leave and stuff like that. But anyway, that's just something that you could always avail of. Other aspects of the class, of course, we can't do that, so just for the project. Okay, and let's see. So those are the main things I had in mind. So again, in terms of the topics from lecturing from our side, it's basically going to be, after the time part is done, it's going to be lecture on security and a lecture on Android. Okay, I might do one more lecture depending upon how the student presentation time comes out, going into sort of a deep dive into Linux itself in terms of how it manages time and its real-time scheduling capabilities and stuff like that. But that I will see after I figure out how much time we need for the student presentations. Okay, so last time around, we had started going into time and clocks and things like that, and I had talked about that how kind of basically a clock consists of some sort of an oscillator and some sort of a readout mechanism, a sort of a counter. So oscillator provides a periodic signal, which somehow we have established a relationship against what we think of as a second, and then the readout mechanism is some sort of a counter. The counter could be at the hardware level, but also at the OS level. The counter is exposed to applications through APIs. So, like in Linux or Unix types operating systems, there are system calls like get time of day or things like that. There are also calls which let you say wait for a certain period of time. So these go under the umbrella of sleep. There are also calls which let you wait until an absolute time. So you can say wait until 5 p.m. or whatever, things like that. And then usually all operating systems provide some access to some sort of timer abstraction. So you kind of start a timer when it fires, some sort of a signal or interrupt or event comes to you. So, so the topic that we started discussing was that how this knowledge of time itself is not perfect, in the sense that because of imperfections in the clock, imperfections in the various parts of the clock, so oscillator as well as the readout mechanism, we end up having an error. And there are two ways of looking at this error in frequency domain. So you can think in terms of frequency accuracy and frequency stability, and then also in the time domain. And in case of time accuracy, it's basically referred to as the offset, and time stability in turn relates back to accuracy and stability, because if the underlying oscillator frequency is incorrect, then even if you started out with a zero offset from the UTC, from the global time, you will drift away from it. And the other thing is, if frequency is unstable, then that offset itself, instead of moving away in a predictable fashion, if frequency offset was constant, then you had a hope you can, in principle, learn it and compensate for it. So if at some point in time in the past I had a known offset, and I also know that the oscillator I have has a fixed frequency, but that frequency is wrong, then I can learn that of a frequency offset and use that in a linear expression from prior point on. The problem that though happens is that frequency itself is highly unstable because it depends upon various environmental factors, and that makes the whole process challenging. The other challenge which comes from is that just the act of determining the clock offset is pretty tricky. So the fundamental problem, as we'll see later on, that we face is the following. So let's say I have a clock, you have a clock, and we want to synchronize a clock at a certain point in time. And let's for the moment assume that the messages from me to you take some fixed amount of time, but I don't know that, and messages from you back to me again take some fixed amount of time, possibly different from the other direction. And now if you try to solve this problem, unfortunately it is an under constraint problem. So, and moreover, our measurement of all this time of flight and stuff like that takes itself tends to have errors. So even so the problem of figuring out time offset and frequency offset suffer from all these issues, but on top of it, the clocks themselves, the oscillators themselves keep drifting. So when you look at these characteristics of oscillators and things like that, in the frequency domain, you can think in terms of the stability, and that in turn you can think of as a noise that is appearing. In time domain, you can think of it as a noise in the location of the clock edge. So upshot of all of this is that by the time we are done, depending upon the application, these issues begin to affect the application's performance. So if your application is sampling the bits in an arriving packet, then the stability of the clock and the error in the clock edges affect bit error rate and how long the packet could be. Likewise, if you're using these things for, let's say, localizing something, GPS type multilateration, then it will translate into location error. So almost in every case, you can think of that the error in time information translates into some sort of an error which is at the application level. So what an application would see as time information then is affected by a whole variety of things. So ignoring this slide and kind of talking in terms of an OS, so let's say your application says get time of the day. What all factors are affecting it? So firstly, the system call itself may take some variable amount of time. So when you make the get time of call system call, at deep down the kernel is picking up the time information from some counter that it is maintaining, and then the information percolates up to you. So by the time application sees that some variable amount of time has passed, so that itself is there, because during that process maybe an interrupt may arrive, things like that may happen. Second thing is that the counter that the OS is maintaining is probably going to be at some granularity. It would have, it's updated at some period, so that's a quantization error that kicks in. Thirdly, that counter that the OS is maintaining, the way these things work is that count, sub-software variable, is being periodically updated by a hardware counter, which in turn is being driven by some clock. So errors in that clock frequency are going to translate into error in the rate at which this counter is updated. Furthermore, we use some time synchronization protocols, things like NTP, which most of our computers use, where this clock is periodically corrected. So the net effect of all of that is that that time information that the OS has is suffering from all those factors that I described. So that information itself is correct. So by the time we see, the application gets to see the time, it has some uncertainty. When you also say things like sleep for 5 seconds, when the 5-second event is up, then all the OS does is it puts the process into ready to run queue, but the scheduler may not give you the CPU immediately. So by the time you again wake up, some additional time may have passed. So there's all this kind of sources of uncertainty. It basically means that at the application level, things can get hairy. Now, if you're dealing with applications where you are talking about tens of millisecond type requirements, all of this is fine. On the other hand, if you're looking at applications where you're measuring some time of flight of a signal between two nodes and all, then you are seeking nanoseconds or some microsecond type delays, and then things become problematic. So in many applications, you have to start dealing with timers and all right at the hardware level. To show how clocks drift, this is an example of some data from, I think it's from Hewlett-Packard. Okay, so what that is showing is there are 3 LCD stopwatches, the type that you commonly can buy in the market. And what they did was they captured, using a camera, they captured what these stopwatches were showing at a fixed time every day, with the camera itself being operating with reference to an atomic clock time. Okay, so the camera is sampling accurately, and now what is happening is at some point in time, the watches were perfectly synchronized, and what you see is how they are drifting apart and what the reality is should be. So the horizontal line is what they should have been, and what you see is that each one of them is kind of drifting away. That's a long-term behavior. You can see that over long term, in this particular case, 140 days, there's a significant drift which has happened, and that is because there is a long-term change difference in frequency. But even even when you if you so this is the cumulative effect of the way the frequencies were drifting. And one thing if you see is that the frequency drift itself is not constant. So it's not as if the drift was happening because there was a constant frequency error, but rather the frequencies of the different watches were varying over time, and therefore you have a more complicated behavior. So we can examine sort of the net these kind of instabilities in various statistical manner. One thing which you can do is you can measure the long-term drift, so kind of the average frequency error, subtract that out, and what you would then be left with is kind of the changes in frequency around that mean. And once you do that, you can begin to look at what the short-term variations are. So there are many different ways of kind of examining this data, but one of the things that therefore one has to worry about is how the underlying clock frequency is changing and compensate for that somehow. And that is what synchronization protocols do. If your clocks are very stable, then even if they are erroneous in the sense their frequencies are different, you can learn that offset and then relatively infrequently revisit your synchronization. If on the other hand, clock frequencies are changing quite frequently because maybe temperature is varying a lot, things like that, then you have to do that synchronization much more frequently. So the villain in the story, I guess upshot is the villain in the story really is the drift in the clock, because all other sources, any constant offset, whether in frequency or time, through some sort of message exchange, you can begin to learn. We'll see that in the next slide set, how one can do it, but both time offset and frequency offset you can learn, and by making multiple measurements, you can learn it to high accuracy. Again, the problem comes because clocks change, and they change in unpredictable manner depending on the environment. So even a simple task, let's say we want the OS to offer application a service along the following lines. Wake me up at 5 p.m. Okay, so just a simple call. Wait until 5 p.m., something along that line. So wait until a future time. So how would you typically implement it? Let's think about that. So what would you do? So at the operating system has some counter, some clock, stuff like that, and the application says, wake me up at a future time, t prime. How would you implement something like this? Anyone?
Well, brute force way would be to just check out how many clock ticks will happen until then, wait that many clock ticks, and then set off an alarm. Okay, so what you're basically saying is, I'm going to figure out, I have a clock frequency, and I'm going to figure out how many by how many ticks would the counter advance, and then arrange for the counter to generate an interrupt when it reaches that value. And you'll have to deal with some nitty-gritties, like your counter may have a rollover period which is smaller than this, so you'll probably do some sort of count of how many times it's rolled over, and then kind of the remaining delta. Okay, so reasonable strategy. The problem with the strategy is that you are calculating how many ticks you need based upon an assumption about the clock frequency. And so you have a few sources of error there. Number one, that assumption about clock frequency immediately raises the question, what frequency are you going to use? So there is a nominal frequency that the clock hardware has, which as I talked about, depends upon manufacturing variation and all. So usually what would happen is that by comparing it against the information from a time server using, let's say, NTP protocol, you would have learned the frequency which you are seeing currently. So you have a better estimate of the frequency, which is the frequency which is right now. So you can say, okay, maybe I should use that. The problem is that if the time at which I have to be woken up is way in the future, then as these plots are showing, the frequency is going to go through lots of changes. So who knows, what might happen is that because of environmental condition between now and that time, 5 p.m., which could be hours or days from now, the frequency may actually have had a slowdown. The clock may have become slower, and therefore I would miss my deadline because I would be counting according to, and I would have counted the ticks according to a wrong impression of frequency. So so you cannot simply kind of do the scheme where for way out into the future you can just calculate things. Somehow you need to keep track of it on a shorter basis and revisit your decision that how many counts should the counter advance by when I should wake up the interrupt. So it's not a decision that you can take at the time application made a request. Okay, so that's so in simple systems where you're trying to measure every millisecond or even every second or something, and your precision requirements are not that great, the approach that we talked about is fine. I compute based upon things. Now, usually what we see is the computation itself is done based upon the data sheet number for the clock. Now, that can be somewhat risky because usually when we, so when you look at a clock data sheet, there are a couple of key numbers that one has to worry about. One number is what is the maximum error from the nominal that the manufacturer says. So that depends upon the quality of manufacturing. So these are crystals, they cut the crystals, so the error in cutting the crystal translates into an error offset in the frequency. And the other promise, and that's expressed in ppm. So they basically say, I'm selling you a 10 megahertz crystal, but by the way, it can have a 10 part per million error, and you can calculate, therefore, what band the nominal frequency is going to lie in. And that would then additionally, they would have some sort of a number specifying how this frequency changes over time. So they may say something like over a band of minus 25 degrees Celsius to plus 50 degrees Celsius, how much would the frequency change by? And that would be the other number, and that would be in the form of how much frequency changes by for a given amount of temperature. The part which you don't know is how is the temperature changing. That depends upon your deployment. So trying to compensate for these things eventually boils down to the big unknown, namely the environment, which you don't know because it lies in the future, and you can seek to predict it after your deployment has taken place. If you are in a stable environment, air-conditioned room and all, it's easier. But if it's an embedded system deployed out in the wild, things can get tricky. So a typical system, if you were to kind of abstract out its flow of time information, it then looks like there's some sort of a resonating element, a crystal, some sort of a circuitry which couples in it. This is usually analog or may have some digital elements, but output of what is what you call, what we see it as a clock signal. So when you buy parts, they usually either you can buy just the oscillators, in which case the clock driver is on your chip, or you can buy the entire oscillator, in which case clock driver is part of the same package. So you have a clock signal that drives some sort of a hardware counter, and then the software would have the ability to set it, read it. Usually the hardware counter would have other things like it can generate an interrupt on a periodic basis, it can generate an interrupt when the counter reaches a particular value, it can do things like maybe it can take a signal from outside, and when the signal arrives, it can take a snapshot of the counters. All those kind of things could be done. Depending upon how many bits you have and what the clock frequency, that gives you two things. The clock frequency dictates the granularity, and the number of bits dictate the overflow. One of the things which has happened in recent years is that even in operating systems like Linux, they have begun to expose time at a finer granularity. So it used to be that you could access time at basically millisecond type granularity because it was fundamentally coming from the internal time variable that the operating system was maintaining. So there is, to do its scheduling, the OS maintains, in case of Linux, they call it the tick. And there's a kernel variable called HZ, Hertz, which basically says what is the duration of that tick. Usually it is set to 10 millisecond, 20 millisecond. So the operating system's fundamental notion of time is basically how many ticks have happened. There is a variable which is advanced every time the tick happens. So if the tick is 10 millisecond, it's updated every 10 millisecond. So it used to be that when the operating system would get time of day, then it was really coming from this counter, and therefore fundamentally it was limited to 10 millisecond, even though data structure may have lots of other fields. But over the past 5 to 10 years, higher precision timers have emerged. So there are ways to make calls that begin to access high resolution timers. So Linux introduced the concept of HRT, high resolution timers, and provided additional APIs to access those. Now, the problem that happens there is that you're still accessing those using the same system call interface. And the consequence of that is while your timer may be very precise, now down to nanosecond in principle. The problem though is that you're accessing it using the APIs, which are a lot more delay prone. So there are a couple of ways one can address this. One way is somehow provide access to the hardware without having to go through the API, without having to go through the system call. And the traditional way in Unix to do that is, okay, so let me back up. Why do you think we cannot just do it? Why can we not simply give application direct access to the hardware? Safety concerns, exactly, right? So we do memory management and have these hardware resources are made visible only to the OS so that an application cannot go and mess up with the timer configuration and all and thereby mess with others. So safety issues prevent, so even for read type devices, traditionally the interface has been there would be a device driver and you would do a read call on that. But in many cases, you can choose to expose this hardware to the application either because it's read-only or it is because you trust that application. So the traditional mechanism to doing it is to go through the memory management unit. You basically say that this area of memory, I make it accessible at a certain address in part of application's address space. So the application can now simply read and write that location. So if there's a counter, it can just dereference a pointer and get the counter value. And in that case, there is no context switch needed. But it comes with these various kind of issues. More recently, Intel has introduced kind of a lighter weight form of system calls. I think it goes under the name of virtual system calls or something like that, which basically provides the ability for applications to access these kind of hardware resources without bearing the overall with the full overhead. So in a situation like this, if you have these kind of APIs and an application needs very precise timing, what it could do is it can directly access the counter, a high resolution counter, and access the time directly. Otherwise, you basically are going to see the whole uncertainty because of the APIs. The other issue, obviously, which if you are dealing directly with counters, you have to deal with the fact that there is an overflow. So the counters are finite number of bits, and somehow you need to keep for longer time duration. Somehow you will have to keep track of that. This is another example of how drifts might happen. So in this particular case, what you have are a bunch of low-end wireless sensor nodes. And what you are seeing out here is that the time error that they are seeing over how their clocks are drifting away. And again, what you would see out here is that this is kind of reference node, but the other nodes are kind of just drifting away. So these things are for real. One way to sort of combat this problem is to use better resonating elements, more stable resonating element. And there you fundamentally end up facing a power versus accuracy and accuracy versus stability versus accuracy, stability versus power and stability versus cost trade-off. So currently, your choices are the following. You can use a standard Quartz oscillator. It's going to be sub-milliwatt and stabilities of tens of ppm. You can use what are called as temperature compensated crystal oscillator, which basically use circuit elements which compensate for the drift that change in frequency that occurs with temperature. It turns out that since quartz oscillators are basically crystals which are oscillating, their mechanical properties can be modeled as a function of temperature. Turns out they're a cubic curve. So you could either have learned the parameters of that cubic curve, or alternatively, you can simply subject this oscillator to different temperature prior to shipping and then note down the compensation. So what they do is, typically what's done is that they would make a batch of oscillators. They would probably suffer from same error because any error which crept in is coming out of the same crystal. They sample some of those oscillators. by subjecting them to different temperatures, noting down their frequency against a reference frequency, and then they put that information in a little ROM inside there. So that's one approach. That's a digital type approach. The other is the analog approach, where you kind of model and have a circuit which sort of compensates for it. You pay for it in power. So you start going up in power, but you start getting down to 1 ppm. Then even better are things which are called as oven controlled crystal oscillators. And these things literally have a little oven inside the oscillator, which is temperature controlled. So kind of the idea is we get rid of temperature problems by basically making sure temperature is stable. They, as you can imagine, consume more power because you may have to heat or cool the oscillating element. And then at the other extreme are the atomic clocks. And atomic clocks, normally when we would think of like they're huge things and all, cost of money and all, but over the past 10 years through program run by a defense agency out here, we now have chip scale atomic clocks. So you can buy these things for around $1,000, $1,500. They consume 100 milliwatt, or I guess, they somewhere are in this range, but they're, and they have what they call as a physics package. Okay, so that it's not a silicon chip. It's really kind of very nicely constructed system with elements where essentially you have some sort of atomic oscillations which are getting captured. Yeah.
Wait, are these power readings a continuous draw, or?
These are the continuous draws. Now the thing, okay, so that's a good point you're touching, which is if my system has to maintain the notion of time, then the oscillator has to keep running, in which case this penalty you will have to keep paying. Depending up, of course, slower the clock frequency, lower is this going to be this number. So if you have a system which is going to go to sleep for a long duration of time, and you are worried about power consumption, then you should be using very slow frequency. So your PCs or laptops and all, they have this thing called real-time clock, okay, which basically is a separate chip, consumes microwatts of power, but its frequency is extremely low. What do you think is the penalty of having a very low frequency oscillator while the system is asleep? It's not as? For what? Low frequency doesn't imply inaccuracy, right? I mean, low frequency just means that I can update the time less frequently, right? I mean, so but it does have an impact on something else, yeah.
So after long periods of time, it'll drift more.
No, okay. So you're confusing frequency and stability. I can have a 1 second oscillator, which is extremely stable. In fact, last time I had talked about the GPS giving out that 1 pulse per second thing. You can think of it as a very low frequency oscillator. Frequency happens to be 1 hertz, but which is extremely stable, right? So the two are orthogonal things. So the question I guess I'm asking is the following, that in a normal sort of platform, to save power while I'm in sleep mode, I would like to use a low frequency oscillator. What compromise am I making by using that?
Precision?
Huh?
Precision?
In what? Precision in what? Yeah, you are, because frequency corresponds to precision of something. Precision of what? What is the application level impact that you would see?
Like precision in like short time, that's right.
Yeah. So let's imagine that I want to time an incoming event and then wake up, or I want to wake up at a certain designated time. So now if I'm maintaining the time with a lower granularity, the precision with which I can do that task is going to go down. So what I give up, so if in the sleep mode, if you are in the sleep mode and you need to either timestamp something or wake up at a very high, with a very high granularity, then with a very fine precision, then you are kind of in a bit of a dilemma. Now, if it is simply a task of saying, wake up at 5 nanosecond after 5 p.m., that you can still handle, because what you can do is you can arrange for a wake up at 5 p.m. and then switch to a higher frequency mode and then count 5 nanosecond from that. On the other hand, if your task was, I'm asleep, an external event comes, then I'm going to wake up, but I do want to know when that external event arrived with a very high precision. That's a hard task, because I don't know when that event would arrive, and therefore, if I am in the low frequency mode, I'm inherently time stamping the arrival of that event with a low frequency clock, and therefore imprecise. Do you think we can improve it some way? So there is an asynchronous event. I'm asleep, presumably operating at a very low frequency clock. An external event arrives. My job is I want to timestamp that external event with very high precision, better than that 1 second granularity. So of course, the answer I'm not looking for is, hey, keep the high frequency clock up, because that would consume power. So can you think of some way we can achieve both the goals? So anyway, I'll let you wonder about it. But usually what ends up happening in systems is we combine fast clocks, slow clocks in judicious ways to achieve these kind of different kind of goals. Okay, but the bottom line is stability costs power, frequency costs power. Okay, frequency translates into precision or granularity, which we can orchestrate things. Okay, and the cost structure is roughly similar. By the time you are into clocks in this territory, these are not things you can just call and buy from DigiKey and all. I mean, usually, since these are also things which have significant military uses, so you have to supply all sort of evidence that you are not going to, basically they cannot be shipped to most countries, things like that. So the deeper down you go, the trickier it becomes to acquire. But you can routinely acquire certain kind of low-end atomic clocks nowadays in this country, although you cannot ship them out; they are illegal to ship out. So timekeeping technologies, needless to say, therefore, have been improving a lot. Some of the most so cesium clocks are the one which currently are used for international standards and stuff like that, but there are things which are even better. The other thing is that the area which has been driving timekeeping quite significantly is high energy physics, because they try to timestamp atomic particle collisions and things like that. And so probably the best technologies for high precision timing are actually out of CERN, the big physics lab in Switzerland. These guys are able to do picosecond type synchronization over 10 mile kind of things. Okay, very carefully designed systems and things like that. So there's a whole project called White Rabbit, and which sort of they've been doing. Interestingly, some years ago there was an episode where there was some evidence that faster than light particles were seen, and it had turned out that eventually the problem was that the timing system was at error. Okay, so you're in a realm where you're measuring such fine timing that things can get pretty tricky. Even so, my research group does a lot of work in this space, and what we also encounter, even trivial things like, I have two systems, they are supposedly synchronized with each other. I want to measure how well they are synchronized. It's not something which is that easily done, because you're trying to monitor a distributed set of nodes and your test instruments are centralized. So you start getting into things like even the speed of light over the cables and all start entering into things. If I'm trying to test that two nodes are synchronized down to a nanosecond is 3 feet, I think. Okay, so and your cables and all have enormous asymmetries, and also it's I guess bottom line is it's this people who work in kind of femtoseconds and picoseconds, they have really their work cut out. Okay, so let's see. So how is all this stability and all measured? So main point again, as we saw, is that these things drift, and they drift over both short period of time and long period of time. So the frequency spectrum had a sort of a of noise had a nice sort of curve. So the traditional metric which is used is something called Allan variance. So we are all familiar with standard variance. Allan variance, the way it works is the following: is defined as 1/2 of the time average of the squares of the difference. Uh, let me skip that. Okay. Let's say what we have is some measurement of clock errors. Okay. So I have a time series of that. What I'm going to do is I'm going to first take an average, I'll construct a new time series which is smoothed over some time interval tau. So I get the new time series, which is the normalized average frequency over a period of tau. And then I'm going to take the variance. So then basically I'm going to take successive samples of that smoothed time series squared and its expected value. The key point out here is that this depends on tau because y's were smoothed over tau. So the idea is if I'm looking at short-term time variation, then I can have a very small tau or tau of just 1, in which case I'm looking at variation in individual samples. If on the other hand I'm looking at long-term variations, then I will make tau very large and I will measure it over that. And this will give me the variation that is occurring over time but at different time scales. Okay, so I can monitor the Allan variance. So main thing is we want low values of Allan variance, but the question that we have to answer is low value over what time interval. So I can have a clock with good stability over short time interval, or I can have a clock which has good stability over long time interval, but may show a lot of jumping up and down over short time interval. So what I mean by that is that if I were to look at the next clock edge, it may be very jittery. But if I look at the average jitter over a long time duration, I may have a very stable clock. Or I can have clocks perhaps which have exactly opposite characteristic. They are giving me seemingly good stability from one edge to another edge, but then they keep drifting and over long time intervals the errors kind of build up. But Allan variance, unlike standard variance, allows us to capture that notion. So you can measure Allan variance and have it over different values of tau to capture the stability of the clock over different time intervals. So for example, I can calculate something like the following. So what I have out here is um, uh, I um, I have a counter which is running with some clock whose Allan variance I seek to find. Separately, I have a reference clock, perhaps coming from a high quality instrument. And what I do is, according to when I thought it was 1 second, 2 second kind of precise time intervals apart, I take a snapshot of that counter. And we can do it in a very precise manner using hardware support and all. And let's say this is the count that I am getting. And what you would see in this case is that if I take this difference between successive time samples, then I get these readings. And they're not exactly the same. They have some changes happening. The last digits 89, 90, 88, right? So there is some jumping up and down which is happening. Some of it is presumably because of the quantization error, but some of it is also because the clock is drifting. So what Allan variance says is the following. So since I'm doing Allan variance over an interval of 3, so the first thing I'm going to do is I'm going to smooth it out over intervals of 3. So I'm going to get these this new time series, which is at 1/3 the rate, but which has these smoothed values, and then I'm going to calculate the difference squared. So pairwise thing. So there was something previously, and this difference square is what begins to give us the summation of that is what will give us our time variance. So Allan deviation is how clocks stability characteristics are represented of any source of time. So you can talk about Allan variance of the clock on my laptop. So what all you have to do is perhaps I can set some the clock on my laptop in a big screen, have a camera, that experiment I described. That camera is triggered by GPS signal, so it takes an image at a very precise time and then work off that. Now, of course, even in that setup, you have issues. Cameras operate at some frame rate. So right there, I have a 30 millisecond kind of an issue, which sort of comes in because the frame rate is typically 30 milliseconds. So maybe I'll need to use some sort of a camera, which is a high frame rate camera, where I could do those kind of experiments and come up with these things. Or alternatively, what we can do is, let's say, some sort of an interrupt pin coming to the CPU of my laptop, I send an interrupt from some external source, conduct that kind of experiment. What you see out here are Allan deviation or Allan variance of different kind of clocks. So, for example, you see GPS, which is out here. What you see with GPS is long-term tremendous stability, but short-term there are jumping up and down, which is happening. Tremendous stability in long-term because GPS clocks are ultimately derived from atomic clocks, which are on the satellite. You look at NTP. So we'll look at NTP later on, but it's a protocol used for maintaining time on our laptops and on our computers. And the way it works is it exchanges messages with time servers. Those time servers themselves usually have a GPS clock on it, so they'll have GPS antenna mounted somewhere outside, the cable running, and a GPS hardware which is driving things. So you can buy these kind of things relatively cheaply, and so you have GPS time. But then what your computer sees is a time which is affected by network characteristics, operating system issues, and things like that. What you see out here is its deviation is quite high. This is logarithmic scale, so it's significantly worse than GPS by 1, 2, 3, 4 order of magnitude. So much less stable. Rubidium is getting into these precision clock territory. So these are the multiple hundreds of dollars to $1,000 plus type clocks I was talking about. And what you start seeing is that it has a very interesting stability characteristic. Over very long duration, it again begins to suffer issues. But otherwise, sort of it shows some very interesting characteristics. These are, I think this is just a regular crystal oscillator, this one. So anyway, different clocks, you can examine the Allan variance, and then you can look at what time scale of stability you are interested in and work with that. So for example, if I was examining stability at order of second or so, then my regular crystal oscillator is as good as my GPS. But if on the other hand, I'm looking at maintaining stability over hours and days, then the GPS begins to show its benefit. So a very common, and the NTP on the other hand, if you look at NTP, it is much worse than my crystal oscillator at short scales. But at long scales, it helps discipline the crystal oscillator because the crystal oscillator will hover in this range only, perhaps even get worse, whereas NTP begins to drive the thing down. So the name of the game then becomes, I would have a local clock whose performance characteristics may be sufficient at some time scale, but then they become insufficient at longer time scales. So then I use some other source of information like a network server or like a GPS to then discipline it. So NTP disciplines the local oscillator or GPS disciplines the local oscillator. So what NTP does is there is a piece of software running on your computer which is talking to these servers, and then it applies correction factors to the time. So it doesn't actually change the clock frequency of your oscillator because that's pretty tricky, although could be done. But instead, it maintains a set of coefficients. And so the idea is that the counter, which is being driven by your local clock, the local crystal oscillator, we apply some sort of a transformation to it. We multiply it by some factor and add some offset. And those coefficients are the one which NTP learns and maintains. At UCLA, interestingly, we are one of the places where there is a local time server. So if you go to time.ucla.edu, that's the time server with a very high precision clock. So essentially, we at UCLA are maybe a couple of hops, one the CSNet hop and the other being the campus hop away from a very high quality time precision. So we could get very good quality access to time just by using that as a time server. So if you're doing any sort of experiment and all, instead of using the default time.apple or time.microsoft or time.google, use the time.ucla because you're very close to that. Not all places have that luxury. So what they do is then they refer to lots of time servers and then take an average of that. I guess here in LA, there is UCLA has one, Caltech has one, so there are several sort of organizations who have one, possibly USC does too. But these two for sure, so you can kind of easily get access to good quality time. Or you can pay around $50, $100 for a GPS board, which gives you a PPS signal and work with it. The only problem is that if I'm trying to do it on a computer inside my lab, then I cannot see any satellites. So I have to then run a coax cable up to outside, and those kind of things become problematic. So the issue with GPS becomes one of the ease of deployment isn't that much. So NTP is very convenient on that regard. We'll see later that there is a new technology which has emerged, something called PTP, Precision Time Protocol. And it provides much better performance than NTP by a couple of order of magnitude, starts getting into 0.1 microsecond kind of territory as opposed to a few milliseconds. And that's a networking technology which has emerged quite a bit. Okay, so let's look at what kind of resonation technologies that we have easy access to when it comes to the embedded platform themselves. While you could certainly buy a $1,500 atomic clock and use it, and there are groups who have access to it, more commonly, the kind of clocks you are going to encounter are much simpler. So simple LC-RC circuits, inverter rings, quartz crystal, MEMS resonators. So these are, I mentioned last time, I think, that you basically use mechanical structures on chips and have them oscillate, and then chip-scale atomic clocks and such. But typical embedded systems, it's going to be the first three or four. Let's see. I'm going to skip these. Inverter rings. These are very commonly found on microcontrollers. Almost any microcontroller that you would buy would have an inverter ring, so on-chip oscillator. Big advantage is that it is up and running as soon as your power supply is stable. Big disadvantage is that it is very much dependent upon the temperature. Another advantage is you can have very high frequencies. So you can on-chip, you can have very high frequencies, but they're very unstable and they're very temperature dependent. So usually, because they can start very rapidly. They are often, when your system starts up and you just want to start executing instructions, that's a good thing to do, a reasonable thing to do. And usually the microcontrollers then have some sort of a signal where you can say that now my external clock is stable, and then you can kind of switch over to that. So the model typically then tends to be, you start up using the ring oscillator, and after a short while you switch to the more stable clock. So this way you benefit from rapid start, so you are not sitting idle, but then once your stable clock is available, you kind of switch over to that. So that brings to quartz crystal, which is the dominating technology currently, although MEMS is trying to catch up. So basically what happens is you can cut the crystal along one of its planes, and then kind of the idea is that you can apply a voltage to it, start mechanical oscillation, mechanical vibration, so to say, and then in turn it begins to start amplifying your signal. So it resonates at a given frequency, which is driven by the mechanical characteristics, and then you use some amplifier circuit to extract that out. They are very stable source with good characteristic, good phase noise, that is the jitter and the edges are less, and they generate frequencies in a very narrow range, so you can kind of pick them out and amplify. They require very precision machining. Most of these things are now manufactured in East Asia. There's very little, I don't think there's much local sort of manufacturing happening, depending upon which what plane you cut at, different frequencies are possible. So when you go and buy a crystal oscillator, it's not like you can say, hey, I need 10.45 megahertz, give me a crystal, because not all frequencies are possible. They depend upon the cuts themselves, and there are certain types of cuts which are made on these crystals, and that result in the type of frequencies and multiples of those that are possible. Another common source which you'll find in low frequency stuff is to actually have a little tuning fork crystal. Okay, so they literally kind of are implementing a tuning fork on chip, so to say, or inside the package. The temperature dependence. Let me look at this plot. So this is a quartz crystal cut along a particular plane of the crystal. So it's referred to as AT cut. There are a few different cuts which are available. And what you see out here are different plots. So these different plots, what they're showing is how the stability varies as the temperature. The different colored plots refer to the manufacturing error. So what it is saying is when I buy a crystal like this, if it has a certain amount of error, I would lie on one of the different curves. So 1 second error, 1 second in terms of 1 over 360 of a degree, cut, error in cut, I will, that's the separation. And with temperature, I have a change, and that these curves are defined by a cubic phenomenon. So any given crystal that I'll have would lie on one of these curves, and the process to learn the characteristic then boils down to measuring the stability or measuring the stability of my crystal at a few different temperatures, so that you can learn the parameter of a cubic curve. You have 4 parameters to learn for a cubic curve, so a bunch of small number of measurements can take care of it. So in theory, we can do all of this. The act of calibrating takes time, and that's why temperature compensated crystal oscillators tend to be very costly. There are a whole bunch of other cuts also. MEMS resonators, that's something new which has emerged over the past 4 or 5 years. And these guys are seeking to create mechanical structures on chip in silicon which oscillate and try to provide, oscillate at a particular resonant frequency, and are trying to achieve quartz crystal type performances. Their intrinsic performance is not as good, but by putting some fancy signal processing, they're able to achieve very good performances, very high stabilities, comparable to crystal oscillators. So in many applications, they are beginning to replace crystal oscillators because the advantage is they can sit on the same chip, their height can be very low. Locally, Professor Sudhakar Pamarthi, his expertise is these kind of things. So they work a lot on clocks of this nature, basically. There are a couple of companies which have made their name around this. Okay, so let's see. Yeah, I'm going to skip these slides. So next up, so after I have my clock signal, next up is that clock signal is typically not at the right frequency. I need to generate clocks of different frequencies out of it before it can be made use of. So you have to divide the frequency, you have to multiply the frequency. Those are a couple of things. So how can I multiply the frequency? Anyone? Division is easy. Flip-flops, at least division by factor of, division by powers of 2 is really easy. And so how can I multiply the frequency?
Each time you detect a rising edge coming in, you send out 2 rising edges or something?
Yeah, but where would I get that from? How would I get a shorter time period of it? Yeah. Yeah, PLLs. So anyone else knows PLLs? Heard that term. Okay. So firstly, clearly, I mean, we talk about processors operating at gigahertz, all right? So obviously, we don't have gigahertz type crystal oscillators or any oscillator at that thing, right? So we achieve those things by multiplying the clock, okay? The other thing you would notice is that a lot of standards and all, like they would have very weird requirement, like USB operates at 408 point some megahertz and things like that. They're very peculiar requirements that come up. Some of them basically arise from the commonly clocks available. Some of them are also have other sources. So how do we get to those clocks starting from what I actually have? So the basic, so again, division by fact 2 to the power n is very easy. If I were to divide by an arbitrary n, the problem that begins to happen is that I cannot have, and I want to have evenly spaced clock edges. Then things get tricky, because let's say I'm dividing by 3, then strictly speaking, my edges will have to lie in between the edges of the original clock, and that is tricky. How could we kind of pull those kind of divisions also off? So this leads to the concept of PLLs, or phase lock loops. And the way it works is the following. I have a reference oscillator, okay, and my goal is to generate n times that reference oscillator. So by reference oscillator, I mean that's my sort of stable clock source. I buy a 10 megahertz crystal or whatever. But I need some n times that. So what we do is the following. We create a voltage controlled oscillator. And this could be something which doesn't have to be very stable and all, some oscillator circuit, but it's voltage control. So we apply a voltage to it and we can change its frequency. What we then do is we take the output of this voltage control oscillator and we multiply, and we need n times frf, so we divide it by n, and we know how to do division, as we saw. So now, so if this guy was operating correctly, then the output of the divider would be a clock whose frequency should match that of my reference oscillator. So then what we do is we create a circuit which detects phase error between this, smooth it out, and then feed it as a voltage signal to the voltage control oscillator. So essentially we create a little control loop, and kind of the idea is that if the control action works as expected, then this thing would stabilize as n times frf, and the error would be driven down to 0. So I could do this divide by n kind of trick this way. More recently, and I was referring to Professor Pomarthy, so one of the things these guys have been able to pull off is, instead of simply an n, I could have a rational number out here. So I could say things like need 4/3 of frf. So I can generate other type of combination. So these are called fractional PLLs. Okay, so there are a lot of advances which have happened. The PLLs could be analog, where this stuff is implemented in analog, or they could be digital, in which case it's all done digitally. So upshot of all of this is that PLLs provide a way for us to generate signals, clock signals of the right frequency. So usually, again, on microcontrollers, you would find that there would be a pretty elaborate clocking block, and it's going to take as the reference either a ring oscillator, which in early stages of the system putting up, or an external oscillator, a crystal oscillator, and then it would have the ability to generate multiple frequencies, some frequencies which are meant for processor to operate at, some frequencies for things like USB bus or a radio or things like that, which all have unique requirements. And the magic happens because of the PLLs. Usually these PLLs are programmable, so you can program these n's, or if it's a fractional one, then both the factors, and then generate a lot of different clocks. So what you would typically see then is that there would be some sort of a clock control register whereby you can control the actual clock on which your processor core is operating, and all of that is happening because you're essentially reprogramming the PLLs. And then there would be PLLs which are generating fixed signals specifically for USB and things like that. So PLLs are the workhorse of making to realize the actual clocks that we end up using. The crystal oscillators come at very specific frequencies only, and they don't necessarily match what we need, and they are relatively low frequency anyway. So I guess to summarize all of this, the main takeaways out of this is, number one, stability is the challenge, dealing with that. Rest of the stuff can be compensated for. So stability, you got to pay for it either by power or cost or some combination thereof. Frequency, clock source within the same technology, higher frequency clocks are going to consume more power. So while the system is not doing anything, you probably want to dial down the clock, but that presents a challenge that when you're waking up, you're losing precision in wake up time. Also, frequencies that you like to operate at may not necessarily be available, so PLLs get used to as frequency transformers to go from the reference to whatever you need. Last time I had mentioned that like our mobile phones and all have multiple crystals, and part of the reason they have is because they're combining sort of chips from different sources, so each one of them comes with their own clock requirements. So the modularity of the design kind of leads to that. In theory, it is certainly possible to have a complete system with a single clock source and then using PLLs to generate the clocks and distribute them. But in practice, it doesn't turn out to be that way. Okay, so now we have the clocks which rest of our system sees, and to some extent they are programmable now. So then comes the question, what happens next? So typically these microcontrollers would provide some sort of a counter timer setup, okay, to which those clocks are feeding. So what does that look like? So I'm going to pick as an example one of the microcontrollers to show that how things look like, and it's very generically similar in other places also. So the clock signal, which is coming out of the PLLs and oscillators and the different circuitry, is now driving some sort of a timer counter system, which the OS controls or the OS lets the software access somehow. So this is the clocking, the way clocking works in a particular microcontroller, which happens to be the one in the embed platform. So at the top left is the main oscillator interface. At the middle left, you see this internal piece, RC oscillator, so there's an on-chip oscillator. And then finally, there is a second oscillator interface, which is meant for the real-time clock. So this is low frequency, very low power. So kind of the idea would be that when the system is asleep, then the main oscillator could be put to sleep and only the RTC stays up. What you then see is a bunch of multiplexers which let you select the clock source. So you can have things be driven by main oscillator or internal RC oscillator. They are feeding to PLL. There are two PLLs. One is the USB PLL, which is non-programmable because it needs a particular frequency. And then there is a main PLL, which is programmable. And you can, again, through some multiplexers, you can kind of generate that. Then it generates a clock, which then you can make it go through the clock divider to generate different CPU frequencies. So somewhere in the CPU, there is a register which basically lets you configure the precise CPU frequency that you need. These frequencies also kind of, these clocks also kind of drive other network, other clocks and all also. The RTC oscillator drives a part of hardware called real-time clock, which is basically a counter in which it maintains year, day, month, hour, minute, second, and usually this part, bottom left part, is powered using a separate battery. So the idea is your system could be powered down, but this RTC clock stays up. So three main oscillators, then main oscillator, RTC, and internal RC clock, and you can choose any one of them to drive anything, and so a high degree of flexibility. What happens after a reset is the following, that after a short while, the internal RC oscillator, so when you apply power, the internal RC oscillator would take a little bit of time to stabilize, but after a short while it will become stable. So kind of the idea is that usually you would see a specification like you must apply a reset signal in the initial part, okay, and that is because even the internal clock takes some time to become stable. So that's what's happening in this initial portion, that you have to wait until the internal RC oscillator is stable, and at that point on you can basically begin to operate off that. Your external oscillator usually is going to take longer time, and therefore you'll have to wait even more, but this way you can do a relatively quick start. In this case, if you see, for this processor, it happens to be 60 microseconds. So roughly 60 microseconds after you apply power, you are good to go if you are willing to operate off the internal RC oscillator, which is unstable, unstable and with a less accurate frequency, but is available immediately. External quartz oscillator might take a few milliseconds, so a couple of order of magnitude difference which might exist. Timers and counters and all. So there's these things tend to have a pretty elaborate system in terms of how application gets to make use of these clocks. So what you see out here is on the bottom side of the slide, you see things like capture compare timers, repetitive interrupt timers. So there are a bunch of different kind of timers that typically this microcontroller provide so that the OS and the software can get to use it. Now, in a Linux type system, only the OS gets to see it, and the applications see it through the more limited Linux API. But when you are doing bare metal programming, usually, so like Embed OS or a typical RTOS, they will probably let you access these things directly or through some minimal software interface. So in case of this NXP microcontroller, there are 4 32-bit timers or external event counters. So you can use these things to generate various kind of periodic signals, or you can use them to count the number of external events. Then for each timer, there are a couple of capture channels, and these get used if you want to timestamp an external event. So you want to know very precisely when did the edge come. So you can say monitor. You can tell a timer to monitor a pin, and whenever the pin makes a transition, you can capture the timer value. There are so-called match registers, and kind of the idea is that you set these registers to a value, and whenever the counter reaches that value, an interrupt is generated. So you can have the counter free running, and you can generate interrupt at specific values. And then you can have outputs also going out, so you can have an interrupt being generated and outputs going out. So variety of things which are happening, and you could generate different kinds of waveforms using these timers. So for example, if I want to generate a waveform which has a particular duty cycle, for example, it should have a period of 1 second, and it should make the transition on the signal at a certain duty cycle point, I can use match registers together with the output pin and then programmable timer to accomplish that goal. If I want to timestamp an incoming signal, so for example, let's say I want to discipline my local clock from GPS. So I can take a GPS thing, take its 1 PPS signal, feed that to the capture channel. So every time the GPS signal comes, I'm going to get a value. I'll get the current value of the counter. And by comparing it against the recent history, I can say whether my clock is running too fast or too slow. And if the clock is running too fast or too slow, then I can apply some correction factor. So I can create some sort of a function which application says what time it is. It basically takes the current counter value as well as the corrective factors and generate a modified value so that the application sees a stable time. So one can generate a stable time out of these kind of facilities. So to make effective use or generate precision timing, almost always you will have to dive and do things at the level of these registers as opposed to working with the OS level APIs, because they are designed for more generic usage. And the final thing is that there are specialized timers which are meant for very specific purposes. So one type of timing signal which is very common in embedded systems are so-called pulse width modulators. So what these pulse width modulators, okay, let me ask you, anyone knows what a PWM signal looks like?
It's a square wave with a variable.
With a variable period. Okay, so why do we want to vary it? Someone else? Yeah.
Ratio to on to off basically gives you how much of signal that you need.
So it's a cheap way of conveying analog data. Okay, so instead of actually having an analog signal, I have a waveform where the analog value is represented by the width of the pulse. Can you think of any other way we can represent analog values in a digital manner? So just along the lines of PWM.
I was thinking bits, but I'm not sure if that's.
No. Then you'll have no. That's pulse position. So pulse width and pulse position are kind of the two main techniques that get used. So you get the advantages of a digital type signal, but you're translating the analog value is now captured in the timing information. Okay, so PWM get used quite a bit, and as I said, motors out here. So essentially, what happens is that you have a H-bridge structure, as they call it, where basically the time for which the power supply is connected to the ground is controlled by the transistors being on through these PWM signals, and therefore the longer duration they're on essentially is supplying more energy, and thereby I'm able to control the motor speed accordingly. So it gets used there. It gets used in power supplies. Switching mode power supplies are basically operating on PWM signals. They get used in also other places like brightness control in LEDs, LED lamps that you get. They usually come up with a LED light controller. They're usually operating on this principle. So very commonly found in variety of embedded applications because it's a very cheap way of conveying analog information. So usually microcontrollers provide direct control for that. So the same timers and counters that exist, they could often be retasked for this purpose. You could do it through minimal software intervention also, but since these are so commonly done, they provide that. There is something called repetitive interrupt timer, which basically lets you generate interrupts at repetitive interval. Since every operating system worth something usually ends up having to maintain time, so there is usually a timer which is specifically meant for the OS to maintain its tick. So in case of this, there is a system tick timer, which the idea is that it has to be it's meant to be used to maintain that OS's notion of time. There is a watchdog timer. What the watchdog timer does is the following: that you load it with a value, it starts counting down. When it hits 0, it causes a reset. And what's the purpose? Someone else? Yeah.
Hardware reset.
Yeah, but why? Why would I want to do it? I mean, that's the behavior. I load it with a value, counts down, hits 0, it resets. And why would I want such a timer?
System is different. Suppose you're waiting for a process to connect and it's not going to come. So you reset your system.
Yeah, okay. So basically, I want to guard against the process software hanging. Okay, so the idea is that if the software hangs, then it will not reach the part of code which disables. So if the software is correctly working, it will start the watchdog timer, and before it causes the reset, the timer would be disabled. Okay, so in a correctly functioning piece of software, if the software hangs, takes longer time, whatever, then we will not reach that stage, and then the reset would kick in. That example of the Mars Pathfinder thing that I've described, that exactly was what was happening there, that the high priority task was not getting to run because of the priority inversion, and therefore it was not able to reach the part of the code where the watchdog timer was disabled. So like we start and we stop, so watchdog timer has to be stopped. So because it was stopped, it was not able to stop it, and that was resulting in the thing, the whole system having to restart, which is what we wanted because there was a problem happening. So you want to restart the system. So watchdog timers are pretty desirable to have to guard as kind of something of the last resort, something bad happening to guard against that. Then there is another timer, which is the wake up timer, and this is the idea that what I mentioned earlier also, that main oscillator takes some time to stabilize. So the idea is that depending upon the datasheet characteristics of my oscillator, I can program this value. So that so when I start out after a little bit of reset delay, 60 microsecond, we start operating off the internal oscillator, and then once the wake up timer kicks in, then we switch the clock to the external oscillator, and now I have a more stable source of clock. So all of this has to be done by the OS. As you can see, a lot of attention. If you look at these chips and all, what you'll find is microcontroller chips. You'll find that the actual processor is a very tiny thing. Okay, I mean the processor core is maybe 10, 15, 20,000 gates. That's it. It's these peripherals which really occupy bulk of the area, because by providing these kind of counters and timers and all, there are a couple of things that you are doing. Number one, you are enormously simplifying the software. But the other thing is level of precision has improved tremendously, because while in principle you could do PWM generation and time stamping of events and all in software, you would take a huge hit in performance because of the delays involved. Whereas by essentially creating these dedicated, almost like specialized timing related processors, you are kind of taking care of that. Some of the platforms like BeagleBone, which I had mentioned, they actually have special units, special processors. So BeagleBone, which is a TI chip, this has something called PRUs, which are specifically meant for such real-time interaction. So big part of embedded processor, what distinguishes them from, let's say, Intel general purpose processor chip and all, is the fact that it has this rich set of functions. If we go back to the slide, you would see there's a whole bunch of other stuff that exists, which again you won't find in general purpose things. Like you see UART, CAN bus, which is used in automotive, I2C, which is another serial bus, SPI, which is a serial interface, goes into 10 megabit per second or so. So besides kind of the timer part, there is also a whole bunch of these interfaces which are very useful for interfacing purposes, for interaction with the outside world. So when faced with these kind of embedded processor, probably the main thing to get most out of it, you have to truly understand what all capabilities it is providing. This particular chip, I think, also has DAC, so D2A converter. It has PWM generation. It has a 12-bit ADC, 6-channel. It has quadrature encoder. And anyone knows what quadrature encoder is?
It's encoded that it has two detectors at many space off, so you detect 4 times as many pulses.
Yeah, so it's a sensor for measuring speed data. Okay, so what happens is oftentimes you need to measure rotational speed, right? So what they do is they essentially create a couple of mechanical disks with equally spaced slots in them, and there is some sort of a light beam. As the motor rotates, those slots come in front of the light beam or block the light beam, and that light beam is picked up by some sort of a detector, and that generates a signal. So now as the motor is rotating, you get a square wave. The period of the square wave depends upon the speed with which the motor is encoding. And the two disks which we have of this nature, they are slightly phase shifted. So if one signal comes before the other, it means the motor is moving one direction. If it's in the reverse, it's moving in the other direction. So you basically get two signals which are both periodic, they are phase shifted, and the frequency tells us the speed, and phase shift tells us the direction. And that is very, very, very commonly available from motors and other similar equipment. And again, you can think of it as a way to convey analog data. Okay, it's basically conveying signed analog values in a very compact form. So since again it is very commonly used in many systems, so there's a support for that also. So you would find such specialized peripherals quite a bit in these microcontrollers, so that again, like again the whole quadrature encoder thing, you could conceivably do it in software through GPIOs, but your accuracies would be horrible. Whereas by making use of these specialized resources, you reduce the burden on the software and you get much better performance. Okay, so that was clocks and time sources and issues around that and how things look like. Okay, so next topic in this whole issue of time is, so now we know what happens at a single node. How can we have a notion of time that is shared across multiple nodes? And that is a problem of time synchronization. So I want to. So what does being synchronized mean, basically? So people refer to synchronization in multiple different senses, unfortunately. So one notion of synchronous comes from just the act of being synchronized to a clock. Okay, so synchronous digital systems and all kind of refer to that. We are not talking about that out here. So being synchronized in that sense means doing things in lockstep with some clock, which could entirely be locally to a node. So that's not what we're talking about. What we are specifically talking about is that the knowledge of time or time-related parameters at two separate nodes, physically separate nodes connected by a network, somehow is shared. But even within that, there are multiple notions. So you could talk about synchronized in time, which means that two nodes have the same concept of time. So somehow, if I were to set an event to both of them at the same time, they will both report the same timestamp. In that case, their time is synchronized. Another one is synchronized in frequency. So what that would mean is I send an event and another event which is a certain duration apart. Both of them will measure passage of time and will report the same passage of time, which means that the frequencies are synchronized. But that doesn't mean they need to have same knowledge of time. They just need to have clock sources whose frequencies are synchronized. So they will report same difference in count between the two events. And finally, there is phase being synchronized. And what I mean by that is, let's say I ask the two systems to generate a square wave of a known frequency. One setting could be they both generate the square wave. The square waves individually have identical frequencies, but they're phase shifted. For them to be phase synchronized, the phases will also need to be the same. So there are these three separate type of synchronization needs that may occur. Synchrony in time, if I have synchrony in time and maintain it, then I obviously also have phase synchrony and frequency synchrony. If I have synchrony of phase, then I also obviously have synchrony in frequency, and then finally synchrony in frequency. So these are kind of the three things that get required, and we don't necessarily in every application need all the most stringent form. So two clocks are said to be synchronized in time at a particular instant of time if the difference in time values that they are reporting is less than some constant delta. Now even here you see I'm using the term skew, clock skew, difference in time values of two clocks. Even there you'll find that some people use skew to refer to frequency error, and some people use it to refer to offset between the clocks. So again, sort of lack of consistency. A set of clocks in a network are said to be synchronized if the error between any two of them is less than delta. So I have a bunch of nodes, and if I say they are synchronized, then I'm basically saying that any pair of nodes will have an error of less than delta. So to be able to synchronize clocks, I would need some mechanism so that I can know one node can know what is the time at another node, and then do something with that. And of course, the problem out here would be somehow communication delay comes into play, right? So if I ask you what is the time, you say time is 10 a.m. Well, by the time I see it, that message arriving, there is some unpredictable delay has happened. So a node always gets to see the time after some unpredictable amount of one-way delay between the two nodes, which we don't know. So if by the time I see the message arriving, there are two sources of errors. One is the fact that we have an offset, and the other is the fact that there was a delay, and the two cannot be separated out. Whether your clock was very behind and there was a long delay, or whether your clock was close to mine and the delay was short, those two cases essentially are identical for purposes as far as I'm concerned. So communication delay, and the fact that communication delay is very unpredictable because of queuing that happens and all becomes an issue. Another issue which occurs in clock synchronization is that I have to be very careful when I synchronize. So let's say I contact time.ucla.edu, I find that my clock is ahead. So one gut reaction would be, okay, let me turn back my clock. So I'll turn back the time. The problem is that can create havoc with software, because previously my clock had certain value and I may have timestamped certain things. Like, for example, I may have timestamped the creation of some file or a database record or things like that. And now suddenly I turn my clock back. So what happens to those timestamps? That can create a lot of problems, because it would appear as if there was violation of security protocols and things like that. So when we synchronize, one has to be very careful about how we synchronize, and the other is we have to be very careful about the challenge of communication. About this latter point, so going back to this issue, so I checked a reference clock. My clock is ahead, and I just told you why it's a bad idea to just turn back my clock, okay, because of all the problems it might create. So what do you think? What's a reasonable alternative solution?
Maybe you can sleep for the time. You know.
That can also, okay, possibly, although that sleep what? Like you seem to be suggesting sleep the whole system, right? Which is not a good idea.
You can slow down the clock.
Yeah, you slow down the clock. So you aim to catch up, or whatever. You aim to let the other party catch up with me, right? So you change you either actually change the frequency of your oscillator if it lets you do that, or alternatively you apply a corrective factor. So you sort of multiplicative factor. There's a transformation that you're going to apply to the counter, and that there is a multiplicative term in it, and then you reduce that multiplicative term. So slowing down, and likewise speeding up. Instead of if I am behind, instead of suddenly catching up and then having this gap of time in which can create problem, you speed things up. Basically, okay. So in Linux, it exposes two types of clocks, among others. One is the standard clock, and that clock actually can go behind. So if you read it, you may see times in which it has a sudden jump, or it may go back to the previous reading, go back from a reading that you saw previously, depending upon sort of what's happening. But then they also have a clock called monotonic clock. And that monotonic clock is the one where they make the promise that you will never see a time that goes back. Okay. In fact, in modern systems, there is so this what I described monotonic clock in Linux is a purely software fiction. Okay, they basically just in modern systems, there is actually one place where, for security purposes, clocks that never go back become extremely important, okay, which is any sort of content, digital content right management or security kind of issues and all. So common now in pretty much, I mean, all our phones and most current generation laptops and all, is that there is a device called Trusted Processing Module, which is a security hardware, which among other things provides a timer which can never go back. Conceptually, not even across power down. Okay, so conceptually what it does is, when you restart the system, its time can only move forward from what it previously was. And that prevents attacks like where you reset the time on your machine to pretend as if you are installing that software for the first time or things like that, or whatever. So those kind of things. So time information has important security role also, which those TPMs provide. But that apart, just in the normal usage, timestamp of database transactions or file system calls and things like that become important. So clock synchronization has to be done carefully, and what we will see is that the challenge in part comes from the communication delay, and of course other challenge is the stability of the clocks themselves, which come into play. So why do we care about time being synchronized? I mean, a lot of these things are fall into almost the obvious category. There's so many applications where we need the notion of time at two different nodes to be reconciled. So, for example, two nodes, and we want to say they detected event 1 and event 2. Could we say about the ordering of the events? So, ordering of events, coordinated actuation. Two nodes have to do something at the same time. Logging the data at different nodes and then reconciling it. For example, you are debugging, and one node says, I changed this variable at this time according to my local clock. The other node says, I did this at this time according to my local clock. You need to reconcile the two. Absolute time of occurrence. So I need to measure speed of a car. I need to be able to figure out those things. Measuring performance. So there are lots of places where multiple nodes need to have a common notion of time. In fact, even for nodes to communicate, as we saw last time, they need to have a common notion of frequency, among other things. They need to meet in time, and they need to have a common notion of frequency so that they can sample the bits. So almost anything meaningful a computer does to interact with other computers or to interact with the physical world requires a notion of time which is either shared between two nodes in the network or shared between the node and humanity's notion of time, okay, so that we can measure time according to some physical value. Lots of examples. Many applications now often are doing things like localization or detecting which direction the sound is coming from. So you see these directional these audio units which have emerged where they fake, without having multiple speakers, they give you the effect of surround sound. Okay, so they basically direct the beam accordingly. Or there are these audio systems. Anyone heard of this Sonos product, which is kind of a distributed audio system for homes? And they have multiple speakers which are very tightly time synchronized, because if they were not, then your ear will hear two separate streams. So lots of applications like these depend upon things being synchronized. When you are tracking something, a missile moving or a car moving across a sensor field, same kind of issues. You have different sensors reporting multiple time stamped events, and then you're going to combine them into some sort of a trajectory using techniques like Kalman filter and stuff like that. Any error in time synchronization in those cases directly translates into an error in time. So this is an example out of Professor Kong Yao's group long ago, where basically they were trying to synchronize mobile devices by having acoustic signals being emanated from other things. And what it basically shows is, as time sync varies, so does your error. Okay, so localization and time synchronization almost kind of go hand in hand. One technique which is very commonly used is that we try to detect the direction from which a sound signal is coming. And kind of the idea is that some acoustic event happens, if two nodes can figure out the direction, then we can do a intersection intersection of the two beams to figure out the location. So the way direction is figured out is the following: that at each node we have multiple microphones. Each microphone, and these microphones are all time synced, and they're kind of in a somewhat distributed array, so perhaps order of a few meters. As the sound wave comes, the sound wave front will hit these different sensors at different times. And by knowing the relative time difference, then you can figure out which direction it is coming from. So for example, if the sound wave was coming from east to west, then it will hit Y first, and then since M3 and M2 are equally far apart, it will hit M3 and M2 simultaneously. So by knowing those timestamps, I can say, hey, it came from east. If the sound wave came from the north, it will hit M2 first, then some delta time later it will hit Y, and then again it will hit M3. So by that I can figure out which direction it came from. So this kind of time domain beamforming is used extremely commonly. And has been used for localization quite a bit. Some number of years ago here at UCLA, there was a pretty cool system where they were deploying it in forests and all, and kind of the idea was that some bird makes a sound or animal makes a sound, we immediately want to localize where did it come from. And at the same time, we also, it was an acoustic array, which would then use these techniques to figure out which direction things were coming from. But even better, the nodes themselves were designed so that they would self-localize, because for this scheme to work, so I get one angle and then I have another node somewhere else and I get another angle. By combining the two readings, I would get the location of the target, but I need to know the location of the sensors themselves. So what this system did was, you would deploy this, so each one of these poles kind of indicate a sensor node. First, what it did was it chirped itself, so it acted like a bird. So each one of them created a sound which everyone else captured. So at that stage, different nodes have readings about the direction relative to each other. And then you essentially ended up with a graph where I have a bunch of readings, and it turns out that there are techniques called graph realization techniques, but basically at the end of it, one would have node locations for each one of the sensor nodes. And then once the system had self-localized, then it can begin to localize the animals and the birds it was trying to track. So this was working in foliage and stuff like that. So pretty cool with sort of 3D localization and all. And this is a place where, obviously, I mean, this is not where GPS and all has any role, because these are birds which are just coming in also. It's not like they are carrying any tags. They are just making sound, we detect it, and then in this particular case, once the bird was localized, they would then also do things like what type of bird it was, perhaps try to take a photo of it depending upon the cameras being installed, things like that. So localization is a great place where timing gets used. And the next one, which I'll cover on Thursday, is medium access control protocols and power saving. So when radios talk to each other, a big part of the problem comes is they have to share the same channel. And if they don't do it smartly, then you waste bandwidth, because the radios are transmitting when no one is listening. And the other thing is they're wasting energy. They're transmitting when no one is listening, or they're listening when no one is transmitting. So a lot of work in, again, the past roughly 10, 12 years has gone towards making radio protocols extremely energy efficient. Bluetooth LE being kind of the most recent standard around it, but this line of research started around a dozen years ago. So with lots of ideas came up, but the key idea being that knowledge of time can help coordinate radios very nicely. So in the extreme case, you can imagine if we had an agreement that a day from now, I'm going to send you a message, and we had very precise clocks, both in time and frequency, then I can wake up a day later and be sure that you will be up at the same time, and then I can and that your frequency would be the same as mine, and I can just start sending the data bits out without any preamble, anything, because we have an agreement. We could almost, part of the reason that those chip scale atomic clocks were developed was to enable that kind of communication. So we're going to talk about that how synchronization can help with power management of radios as kind of another application before we kind of move on to synchronization protocols themselves. Okay, so let's continue this thread on Thursday. My office hours today are from 2 to 3. So, and if that, so are you guys going to come at 2 or come at 6?
2 works, but are you available to walk
Am available to what?
on the way out to the
Yeah, on the way out we can talk to. Yeah.